Hello everybody. So for today's lecture we're going to talk about exponential functions. This is going to be a new type of function for us, right? We've talked about quadratics already, linear functions. Now we're just going to add a new one to the list. Then we're going to follow up with a discussion about the graphs of these functions. Briefly mention e, and e is a special type of number, kind of like pi. And then we'll end today with a discussion of compound interest and application using these exponential functions. So let's go ahead and get right on into it. Alright everyone, so let's go ahead and give a definition to what we mean by exponential functions, since we're going to be talking about them for today's lecture. So we say the exponential function f of x with base a is denoted by the following form. F of x equals a to the power of x. Alright, so unsurprisingly, we call these exponential functions, and the big idea of them is just exponents, right? So the main change to what we've been seeing before in this class is before we would have dealt with something like this. X squared, so a variable taken to a number power. For exponential functions, we're just changing the script. Instead, we're going to have a number taken to a variable power, alright? So in other words, now, for today's lecture at the very least, what we'll see is something like 2 to the power of x. Alright? So that's the main idea behind these exponential functions, is just changing the script. So again, all it really is a number taken to a variable power. The variable is now our exponent. And then there's the key word here that I probably will throw around a lot from now moving forward, is this idea of base. Whenever I'm referring to base in regards to exponential functions, and actually I'll be using that word in our next lecture as well, but for today's lecture, base, all base is referring to is the number that has the variable exponent. So for this generic answer or example, the base is this value a. In this example down here, we have the 2, so this would be, ooh, my arrow is horrible, this would be base 2, alright? So base, yet again, is just the number with the variable exponents. We can go and write that down. So, base is the number with variable exponents. Okay? So, that's the general form of an exponential function. Of course, we must have restrictions on this. Of course, there will be restrictions on this. What are these restrictions? Well, we say that the value of a has to be positive. So a can, actually, the value of a has to be greater than 0. So even more strict. Just positive. 0 is not really positive. Yep, the value of a has to be positive. And then we have this added condition that a cannot equal 1. And then just at the very end, we tack on that x has to be a real number. Just a quick review. Remember, in case any of you forgot, this fancy e I wrote, this equals n, and that, ooh, I'm running out of room. Let me just write it up here. Yeah, so just quick review. This fancy e I wrote, this means n, and that fancy r I wrote means real numbers. Alright? Yes, so for exponential functions, it has to be the case that whatever your base is, your base has to be greater than 0, and your base additionally can't be 1. Okay? Now that's actually a question worth exploring. Why is it that our base can't be 1? So let's go ahead and discuss that real quick. But, of course, as you can see, right out of board space. If you haven't done so already, go and pause the video now to get this all copied down. Then we'll go into a quick discussion of why is it that a can equal 1. Okay, so let's explore this question. Why is it that we don't want a to equal 1? Well, let's go ahead and see what happens when I plug in 1. So, if I want a to equal 1, then I'll simply get f of 1 to the power of x. Okay? So I have f of 1 to the power of x. Well, let's think about that. Alright, let's contrast that with our previous example, which was f of 2 to the power of x. Well, let's just try plugging in some values. Alright, well, actually, you know what? Let's call this, instead, let's call this g. And let's just make a list of tables, and let's see what happens. So we're going to have x, then we're going to have f of x, then we're going to have g of x. And let's just think of some numbers to plug in, alright? let's try plugging in 1. So if I plug in 1, I get 1 to the power of 1, which is 1, and I get 2 to the power of 1, which is 1. Alright? Let's plug in 2. If I plug in 2, I get 2 to the I get 1 to the power of 2, so 1 squared, which is still just 1. I get 2 to the power of 2, which is 4. Let's try plugging in another number. Let's plug in a negative one. Let's plug in negative 3. So I get 1 to the power of negative 3, and I get 2 to the power of negative 3. 2 to the power of negative 3 is 1 over 8. And 1 to the power of negative 3 is just 1. Okay? And hopefully at this point, you're kind of starting to see the reason why we don't want a to be 1. Because look what's happening here. I have 3 different x's I plugged into these 2 functions. For the 2 to the x function, I got a bunch of different outputs. Things are changing. Stuff's happening. However, for the 1 to the power x function, my f of x, every single x I plug in just makes 1. The output's still just 1. And so, it's kind of misleading wording on the part of the definition, because you kind of read it as a can't equal 1, but the real meaning is not that a can't equal 1, but there's no point in letting a equal 1. So, and as we can see, the reason why why there's no point is because if a is equal to 1, no matter what x you plug in, it's just going to equal 1. Alright? So, what I'm really trying to get at is that 1 to the x is just going to be 1. Nothing happens no matter what x you plug in. Stuff just doesn't change. And so that's why, going back to it, it's not really that a can't equal 1. Nothing bad happens when a equals 1. Nothing bad happens. But nothing happens. Sorry, it's not that nothing is. It's not like anything good's happening or anything bad's happening. Nothing is just happening. It's kind of boring. It's trivial. So we don't bother even talking about it. We just say, forget it. Right? It's kind of pointless. So just nothing happens. So yeah, I just wanted to point that out because the wording of the definition is a bit misleading. Again, it's not like the function blows up if you let a equal 1. It's boring. Nothing goes on. There's nothing really to talk about. So we just say forget it. Just don't let a equal 1. All right. So with that out of the way, let's go ahead and move on to our next discussion. Let's talk a bit about the graphs of these functions. Okay, I lied. Just realized that before we actually start talking about graphing these functions, there is a need to talk about how you evaluate these functions because well, we'll go ahead and see. So let's go ahead and just start this example. Let's evaluate the following function. F of x equals 4 to the power of x. Again, just so we're familiarizing ourselves with its notations, this is an exponential function with base 4. Okay? So, let's go ahead and just try evaluating that. Let's just evaluate with different values. For example, what would f of 3 equal? Oh, man, I had one of those moments where I had to sneeze, but the sneeze wouldn't come out. God, that sucks. Alright, we're going back to it. Let's try doing f of 3. Again, we want to evaluate the function. What does that mean? It means take the value we want to substitute in for x and simply do that. Wherever we see an x, write this number 3 instead. So we're going to have 4 to the power of 3. Alright, just as review, that means 4 times 4 times 4. So that's 16 times 4, that's 64. So we get 4 cubed, or f of 3 equals 64. That's not too hard, right? We've done it before. We've dealt with exponents like this. Nothing new. Nothing that's real challenging. However, where things get a bit tricky with exponential functions is when you consider the following examples, right? What if I was to ask you, what is f of 1.3? Okay? Or what is f of square root of 2? Now that's where things kind of get weird, because let's just walk through, right? If I want to find f of 1.3, that simply means I need to replace x with 1.3, so I have 4 to the 1.3 power. That's where we kind of just scratch our heads and are like, what? A decimal power I don't know how to do decimal powers by hand. Alright? Yeah, that's just weird. And same thing here. This would be 4 to the root 2 power, okay? Yet again, I have no idea how to actually calculate that by hand. And so that's why, for today's lecture video, and also tomorrow's lecture video, basically whenever we're using these exponential functions, it's very important to have a calculator on hand. So for us, for our class, that means we need to have a scientific calculator. If some of you were using the more basic calculators that just did operations, I don't honestly know if they do what we're going to need for the class moving forward. I know scientific calculators will, and we are allowed them for the class. So if you don't have a scientific calculator, you may want to consider getting one for homework and for the final exam and stuff like that. But yes, for this class moving forward, we will need to use calculators to calculate values like this, 4 to the power of 1.3. Now, I would like to explain to you all how to use your calculators and show you how to calculate values like this. The issue being, you're not here right now. I'm talking to myself. So I can't show you how to properly use your calculators if you don't already know how to do this. So that is why, and it's different for each calculator. Like right here, I have a TI-30X, so I would know how to do this first example right here, just to walk you through in case any of you have this calculator. To take 4 to the power of 1.3, I would do 4 on the calculator, and then there's a upward pointing arrow button that looks like this. This is the button you press for power or exponents. This is the exponent button. Okay? So I would press that, then I would write a parenthesis. So here, I can actually write for you what I would write in my calculator. So on my calculator, it would look like this. I would do 4, the arrow, I would write a parenthesis, I would do 1 divided by 3, and parenthesis. This is what it would look like on my calculator. And I would get a value of, I'm going to go ahead and erase this actually, see if you have a similar calculator to me, pause the video, get this written down if you don't already know how to do this. Okay, and so I get a value of around, and we're going to have to round because this is going to be a decimal answer, 1.587. Okay? And same thing for this one. This one it gets even more complicated because again, what I would have to do is I would have to access the square root function on my calculator, and that's going to involve using the second button. Most scientific and graphing, actually I think all scientific and graphing calculators have a second button, and the second button lets you access all these blue written functions. So again, I'm not going to be able to be there to show you how to use your calculator. If you want, actually, I'd be more than happy to meet through Zoom, and if you show me what your calculator is, I can walk you through how to use it. Short of that, please make sure, if you don't know how to properly use your calculator, take some time during this week to go ahead and just Google search your calculator, watch some YouTube videos on it. There are plenty of them out there just to walk through how to use whatever calculator you may have, because we're going to need to know how to do things like this on our calculator moving forward. Okay? So actually, as a good test, I gave you guys the first one. Go ahead and pause the video now. Try to find this number in your calculator. After you unpause it, I'll get what I get on my calculator, and if you can match up, that'll be great. It already shows you'll have a decent understanding of how to use yours. So go ahead and pause the video now. Okay, so let's go ahead and see what I'm going to get off this calculator. So 4 power 2. Okay, so I got approximately 7.10299. Okay, so there it is. Hopefully you got the same thing on your calculator. If not, make sure, double check how you're inputting with parentheses. Parentheses are going to be very, very important when you're inputting in calculators. So make sure you have them in the proper places and the right number of them. But if you if you still don't get the same number as me, let me know through email, and we can try meeting on Zoom, because that, I'm fairly certain, is the correct number. So we got to all make sure we can at least get something like this off our calculator. But short of that, just wanted to briefly mention this idea of the challenges we're going to face when trying to evaluate certain exponential functions. Now, finally, though, with this being said, let's go ahead and talk about the graphs. Okay, so to begin our discussion of the graphs of these exponential functions, let's just go ahead and graph the previous function we're looking at, 4 to the power of x, okay? So if we go ahead and create a list of points off to the side right here using the values for x, -2, -1, 0, 1, 2, 3, we're going to get the corresponding function values of 1/16, 1/4, 1, 4, 16, 64, okay? So this will make a list of points. Plotting those points gets us this on our x and y axis, all right? Feel like it needs to be said, totally understand this is definitely not to scale, all right? But regardless, with these points plotted in there, we can go ahead and see that the general sketch of the graph will look something like this. Okay? And so what we'll come to understand is that this basic shape is what is going to be what defines the shape of all exponential function graphs, but we'll get to there in a second. For now, I just wanted to bother talking about this graph in particular. There's a couple things we can note from here. All right? First thing to note is our Y-intercept. Our Y-intercept is right here. So we have a Y-intercept at the point 0, 1. All right? Next thing to note is that look at the difference of what happens on the positive and negative side for x values. On the positive side of x values, watch. We start at 1, we get 4. We go to 2, we get 16. All right? We go to 3, we get 64. This thing is growing fast. It is shooting up faster and faster and faster. It's not really growing at a steady rate. What I'm trying to get at is if you imagine a line, the line's growing at a steady rate. Each point is like the same distance away from the previous point. As that constant slope, that stepping motion. Not the case here. This thing is shooting for the stars. It's growing fast, all right? That's going to be a defining factor about exponential functions is how fast they grow. And conversely, on this negative side, look what's happening here. At -1, we have 1/4, and -2, we have 1/16. So here where the numbers are getting bigger, on the negative side, it's going to do the exact opposite. The numbers are going to get smaller and smaller and smaller, and they're going to get smaller at a faster and faster rate with each x you use. So this is going to keep on getting smaller and smaller, and approaching this x-axis, they're going to approach that value of 0. Now what I've tried to sketch right here, and what's going to be very important to note, and you're going to have to take my word on it for now, is that portion of the line right there, the portion of the graph right there, will get closer and closer to the x-axis, but it will never cross the x-axis. So the graph will never cross the x-axis. And a quick thing to note is if the graph never crosses the x-axis, that means the graph or this function will never have negative values, right? No matter what x you plug in, that function value will never be negative. That's an important thing to note if we're going to make the claim it never crosses the x-axis. Okay, so there's a lot going on here that we can take note of. And we'll go ahead and spend some time talking about that. But before we do that, before we spend our time talking about that and we get more of a general view for these functions, I'm going to spend some more time talking about this claim right here. Because the evidence I need to support this claim that it'll never cross the x-axis is going to be the fact that this function has something known as an asymptote. All right? Now, I know we've never talked about that before, so we're going to take a quick side tangent in today's lecture, and we're going to spend some time to introduce this topic of asymptotes and how we need to understand them to fully understand the graphs of exponential functions. So let's go and talk about that briefly now. Okay, so to get into our brief discussion about asymptotes, first, the general idea behind them. So the general idea behind asymptotes is this. They are lines that the graph of a function will never cross. All right, so it's going to be some imaginary line on the graph of your function, and you'll see that if you plot the function, that it will never cross that line. So there are a couple types of asymptotes, but for this class, we're really going to be sticking, or need to be concerned about 2 types. And the one we're going to talk about today is the horizontal asymptote. Okay, so let's briefly talk about what this is. Well, so we can kind of piece it together without even me writing the formal definition, just by understanding that, again, asymptotes are lines, okay? So if I'm talking about a horizontal asymptote, I'm going to be talking about a horizontal line, right? A flat line. And what type of lines are flat? What type of lines give us just straight across on our 2D xy axis? Well, it's going to be any constants y equals line. So something like y equals 2. It gives us a flat horizontal line. So that's exactly it. So the line y equals b is, oh, that's a horrible b, is a horizontal asymptote of a function f of x. If, okay, so I'm going to have to introduce some mathematical notation, so I'm just going to write it all out and then we're going to discuss it, alright? So it's going to be this. Alright, so here's the general definition of a horizontal asymptote. We say the line y equals b is a horizontal asymptote of a function f of x if, now, I have f of x arrow b. So in mathematical language, this means if, and I guess I should put the word as. Oh, no, never mind, not as. Sorry. Okay, so this is how we read it. This is read as if f of x approaches b, so that arrow means approaches. If f of x approaches b as x approaches infinity or x approaches negative infinity. Okay? So we're going to have some constant y value. And we're going to call this constant y value, the line along that constant value, we're going to call that the horizontal asymptote. If our function is approaching that value, getting closer and closer to it, as x gets closer and closer to one of the infinities, but what we'll see is that it never actually gets to equal that constant value. Now all of this is kind of meaningless without a visual example, so I'm going to go ahead and draw one now, but of course to do that I'm going to need some board space. So if you haven't done so already, pause the video, get this all copied down. Then we're going to go and I'll put that visual example up on the board. Okay. So here we are, visual example for a horizontal asymptotes. Right, so if I have the value b, okay, then we're going to call, and we call this value b my horizontal asymptote. Then what that means is we're going to be imagining some imaginary line cutting across b. And we're going to call this a horizontal asymptote if we take some function f of x, and f of x has either one of these behaviors. Okay? So what we can see is going on right here is that going this direction, right? X is approaching infinity. Oop, forgot the ing. X is approaching infinity, right? If you keep on marching this way, X is getting going to run towards that infinity value, and what we can see is that that function value f of x. So this is our f of x. What we can see is that our f of x, the function value, is getting closer and closer to that b value, but it's never going to touch it and it's never going to cross it. So x is approaching infinity, and f of x is approaching b. So that's the big idea. So again, just I guess to iterate it, big idea. As x approaches infinity, or in other words, as x goes to infinity, the plus minus infinity, f of x goes to b, but will never equal b or cross b. So that's the big idea for these asymptotes, or at least for the horizontal asymptote, I should emphasize. So that's what's going on there. Okay, so let's go ahead and just do one quick example of a function that has a horizontal asymptote, and then we can move back into our today's lecture for regards exponential functions. So if you haven't done so already, pause the video, get all this copied down, and we'll do a quick example. Okay, so just for a quick example, and it won't be hard to see the idea of the horizontal asymptote here. If we consider the function 1 over x, okay, then its graph looks like this. Let me go ahead and do the graph in blue. Okay, so this is in blue is the graph of f of x, and this graph does have a horizontal asymptote. So what I encourage you now is just go ahead and think for a second, pause the video, see if you can identify what the horizontal asymptote is for this graph. Remember, it's a line y equals some number. So what is that line? So go ahead and pause the video and give that a quick thoughts. Okay, so hopefully what you're able to see and is that the horizontal asymptote is the line y equals 0. Well, why is that? Let's just visually try to identify where the asymptote is, right? So here's our positive infinity direction. We're looking at the graph of f of x. As that x is going more to positive infinity, f of x is getting smaller and smaller and smaller, and it's approaching the x-axis, right? So as x goes to infinity, f of x is going to the x-axis. All right? And what we have to all remember is, what is the x-axis? It's all the x values. What does it mean to be a point on the x-axis? If you are a point on the x-axis, you must have a y value equal to 0. Hence, another interpretation of the x-axis, it's the line y equals 0. So, therefore, y equals 0 is the horizontal asymptotes for this function. Okay? So yeah, horizontal asymptotes are usually quite easy to see visually. You can, at the very least, you can identify an asymptote exists visually without much difficulty. Maybe harder to identify what the actual asymptote is, depending on the number. But besides that, here's our quick discussion of horizontal asymptotes. As I already mentioned, there are two types of asymptotes we're concerned about in this class. If one of them is horizontal, hopefully it's not too much of a stretch for you to understand that the next one we're going to talk about is vertical asymptotes, and that'll be for next lecture's video actually. But for now, here will be the end of our aside. Just wanted to introduce this concept of asymptotes. Let's now get back to exponential functions. Okay, so let's go ahead and talk about the graphs of exponential functions, and let's go ahead and generalize it a bit, and let's give some observations about what we can expect for all exponential functions. Okay, so there's going to be two big types. There's going to be f of x equals a to the power of x, or we'll just say a is greater than 1, and then we'll have the other type, which is g of x equals a to the negative x, where a is greater than 1. Okay, and so we get the following two images. For the a to the power of x, or for f of x, we get the function that is increasing, and for the g of x, we get the function that is decreasing. All right, and so unsurprisingly, these are our two common types of exponential functions, and we call this one exponential growth, and then we call this one exponential decay. All right, but regardless, these graphs have some, regardless of the a we have, there's some defining characteristics that we can make. There's some generalized statements we can make about this graph. First and foremost, its domain. Right? What is the domain of this function? What are all the valid x values? Well, hopefully we can remember, domain basically means what values of x do I not want to use, or in other words, visually that comes into like breaks on the graph or places where the graph doesn't use certain x values. But what we can see here is that this is a smooth, continuous graph, right? no matter what x I choose, it's going to end up on the function somehow. So what that translates to is that the domain of exponential functions comes out to always, or generally always, be all real numbers minus infinity to infinity. Now, however, the range of this graph or the function is, as we're called, the range is the valid y values. Now, conversely, just reading off visually, right, we can see that the graph never touches this negative y, or never uses these negative y values. So the domain of this graph is actually going to be 0 to infinity. And what we'll see is, remember our discussion about bracket and parentheses, we're actually not going to use the 0, so we're going to write it with a parenthesis. It will be the case that this function never equals 0. Okay? So moving on to there, we can make note of the y-intercept. The y-intercept of this graph, remember the y-intercept is the point in which we cross the x-axis. We can see quite clearly it happens at the y value of 1. So our y-intercept is the point 0, 1. And that y-intercept point is something I want to go and pause and talk a bit more about. All right? So what I'm trying to get at here, and this is actually pretty important notes, is that no matter what your base is, no matter what value of a you choose, the y-intercept will always be 0, 1. All right? So no matter if that a is 3, no matter if that a is 4, no matter if that a is 10, no matter if that a is 10 billion, the y-intercept will always be 0, 1. All right? Now, why is that? Well, let's recall. We are taking our base and we are raising it to a variable power, that variable being x. Our points are always x, y. For a y-intercept, to be a y-intercept, you must have an x value of 0 for the point. Okay? So if I want to talk about the y-intercept for an exponential graph, I know I need to be plugging in 0 to my function, because I want the point where x is 0. So no matter what that base is, I'm going to have some number a to a power of 0. Now for us, that's pretty neat and worth noting, because we understand through our properties of exponents that anything to the power of 0 equals 1. In other words, no matter what the base of your exponential function is, it will always have a y-intercept at 0, 1, if it is the form. Now here's the catch. It has to be solely of this form. It has to be a to the power of x and nothing else, right? If it's a to the power of x plus 1, not going to fly. So if it looks in this form, where it's simply just some number taken to a variable power, then we can guarantee its y-intercept will be 0, 1. If we do things to this function, add or subtract numbers, things like that, that's not the case anymore. We've got to be a bit more careful. But I just wanted to point that out. So we have the y-intercept. Something else we've already kind of mentioned here, this is an increasing function. Something we also mentioned is that this is continuous, so it's increasing and continuous. Right? Remember, continuous means there are no breaks in our function, no breaks in our graph. And the last thing important to note is, again, tying in this idea of asymptotes. This function does have an asymptote. I've already alluded to where the asymptote is, so I actually encourage you to pause the video, think for a second real quick. What is the asymptote for this function? What is the horizontal asymptote? Y equals what? So go ahead and think about that now. Okay, so I kind of already alluded to it, and where I alluded to it was right here at the range. I said when we were discussing the range, I said that the function will never equal 0. Now remember, for our asymptotes, we can never cross that value, and we can also never equal that value. So yes, it is a case that this has a horizontal asymptote at y equals 0, or in other words, the x-axis. This function has a horizontal asymptote. All right, so here are the, 5/6 defining features of exponential functions if they have this form. They have a domain that uses all real numbers. They have a range from 0 to infinity. They have a y-intercept at 0, 1. They are increasing / continuous. And they have a horizontal asymptote at y equals 0, or in other words, they have a horizontal asymptote at the x-axis. Okay, so going on to our next exponential function, or exponential decay, we can see that it has a lot of the similar traits. Its domain and range are the same, right? It's the same image, just kind of turned around. So the domain and range don't change here. So domain and range are the same. Also, it has the same Y-intercept. So same Y-intercept. Right, again, not surprising if I have some base a to the power of negative x. Again, the y-intercept is where the x equals 0. So I'm just plugging in 0 to that function. I'm going to have a to the negative 0. Negative 0 is just 0. So I get back to the same situation I had over here. No matter that base, that a to the 0 will equal 1. So the y-intercept will always be 0, 1. Okay, now here's where it gets different, because where this is increasing, hence exponential growth, this is exponential decay, so this is a decreasing function. But it is still a continuous function. It is a decreasing continuous function. And lastly, again, it does have a horizontal asymptote. I guess I should number these, right? 1, 2, 3, 4, 5. Okay, so this also has a horizontal asymptote and has it the same place at that line y equals 0. So here's just some generalized characteristics we can make about for exponential functions with this form, with our two big types being this growth and decay. So go ahead and copy these down, and let's move on to a couple more examples involving graphing these functions. Actually, hold the phone. I forgot to mention a very important point. That point being, and I'm going to need some board space, so actually I'm going to go ahead and erase all this bottom stuff. So if you haven't already, copy that bottom stuff down, and then I'm going to move on to the point I want to make. So go ahead and pause the video. Okay, so let me erase this. And the point I want to make is there is a connection between f of x and g of x. Something we already talked about in this class. Alright? So f of x and g of x, there's a relationship between them. Go ahead and pause the video and think about what is the relationship between these functions. It's something we've talked about before in this class. Flip back to your notes. And just think, visually, f of x is the function that looks like this. And g of x is the exact same function, we've just flipped it around. And there's the key, there's the hint right there. We've just taken the image and we've flipped the image. This is something we've discussed before in this class. So I encourage you actually to pause the video and try to think to yourselves, what is the connection between f of x and g of x? So go and do so now. Okay, so hopefully you put through your notes, and hopefully you came to the realization that f of x and g of x are reflections of each other, right? Remember that whole day we talked about translating and reflecting graphs? That's exactly what's going on here. F of x and g of x are reflections of each other. In regards, remember when we're talking about reflections, we have to emphasize which axis we're talking about. Which axis we're reflecting across. And for us, this is a reflection in regards to the y-axis. In other words, we took our image and we folded it over the y-axis. And that's how we connect both of these. All right? So on this topic of reflections and translations, this material we've discussed before, let's move right into our next example. Okay, so for our next example, let's just go ahead and graph the following function. F of x equals 4 to the power of x minus 2. Now, as I talked about, or as I briefly mentioned, this is a translation of the original function we talked about for 4 to the x, right? So if we consider 4 to the x our parent function, then this function is just a translation of that, and of course, since we are subtracting a value away from the function. That means we are translating the function. This is a shift. This is a vertical shift. All right? This is a vertical shift 2 units down. Just to review, when you add or subtract to the parent function, that is a vertical shift up or down. When you add or subtract to the variable, that is a horizontal shift left or right. So since our parent function is 4 to the x, and I'm subtracting 2 away from that parent function, this is a vertical shift 2 units down. So, if I wanted to create a quick sketch of this graph, that's not too hard then. So it's not too hard to create a sketch of this graph. So before I had a y-intercept at the point 1, 0, or 0, 1. Right, I'm now going to shift that point 2 units down, so I'll go to 0, -1. So I'll now have a new y-intercept at the point 0, -1. Okay, now, in addition to that, well, let's go ahead and create the quick sketch. So I can then sketch this graph, and it'll look something like this. Right, same exact shape, we're just going to move it down 2 units. So we're getting something like this. Now there's something that's very important to note about this translated image. Something we have to make special note of. Ooh, don't like that. Give me 1 second. That's better. Okay, so what's important to note is that so let's do a little aside here. So for our parent function was 4 to the x, all right? And so it had some graph that looks like this, with its y-intercept right there. But what's important to note about this image is that it's horizontal asymptote. This being that general form we talked about, with it solely being a number with a variable power, this means its horizontal asymptote had to be the y or x-axis, y = 0. Okay? And we know that is the horizontal asymptote because the graph of that function will never cross or equal y = 0. However, for this new function, for this translated function, it crosses the y-axis. Let's actually mark that in red. It crosses the y-axis. Oh, my bad, not y-axis, x-axis. It crosses the x-axis. So, by definition, to be an asymptote, you have to be a line the graph never crosses. That already tells us that the horizontal asymptote for this function can no longer be the x-axis, right? So the question stands, well, does it still have a horizontal asymptote? And hopefully my sketch is clear enough where we can kind of get the impression that it does, right? The graph is moving down, and it's moving along, but it doesn't continue going all the way. It doesn't just start going straight down, right? We can start seeing it starts flattening out. So that to us implies, that's a visual, kind of visual hint that a horizontal asymptote still exists. But it's not at y = 0 anymore. So the question then stands, well, where's our new horizontal asymptote? And it actually isn't too hard to figure that out. Just, again, go back to the general idea of this whole example. What is this example doing? Well, all it's doing is taking our original parent function and shifting it 2 units down. So, with that in mind, just go back and understand that our parent function is not only the graph right here, but the parent function actually includes the asymptote, because the asymptote is a key feature about this graph. So when we're talking about the parent function, when we're talking about the parent graph, not only are we talking about the curved line, we're also talking about the asymptote. Kind of think of them as being one graph. So in other words, to go back to this translated graph, if all we've done so far is take the curved line and translate it 2 units down, well then our horizontal asymptote, it's going to be the same idea. Just take the original horizontal asymptote and shift it 2 units down. In other words, this function f of x has a horizontal asymptote at the line y = -2. Okay. Again, we've done a vertical shift on our parent function, and so what that basically means for us is you're going to do a vertical shift on the horizontal asymptote as well. You're just going to bring it down the same number of units. And that right there is going to be an important note for today's lecture, is that in regards to exponential functions, vertical shifts also change the horizontal asymptotes. So vertical shifts change the horizontal asymptote for exponential functions. Okay? So that's definitely an important note for today's lecture, definitely important notes for today's lecture is whenever we're graphing these exponential functions, if you identify a vertical shift being present, that means you need to understand that the horizontal asymptote has changed as well. It's no longer going to be at the line y equals 0. It's going to be at a new place depending on whatever that vertical shift was. Alright? So, with that example out of the way, go ahead and take a moment to pause the video, get this all copied down, and let's do a couple more right afterwards then. Okay? Okay, so for our next two examples, let's consider the following functions. F of x equals 4 to the power of x plus 2 and minus the quantity 4 to the power of x. Alright? So for these examples, I want you to go ahead and try doing both of these on your own. And as you do them, take note of where the y-intercept is and what the horizontal asymptote is. Okay? And also, before you start working on them, remember, these examples we're doing right now are just incorporating the our previous lecture about translating and reflecting functions. So there's actually no need to plot a bunch of points and create a table and stuff like that for these two examples, because we understand what the parent function is, or what the parent graph looks like, that being 4 to the power of x. So with that knowledge, just apply the proper translations that are required for both these examples and create a quick sketch. So with that said, go ahead and try working on these examples now. Okay, so let's go ahead and discuss them real quick, right? So in our previous example, we had 4 to the x, that quantity is minus 2. So in other words, we had our parent function, we were subtracting away from that parent function. That told us we were using a vertical shift. It's the opposite case here. Here, we are adding directly to the x variable. That means we're doing a horizontal shift, right? So this is a horizontal shift. And of course, horizontal shift is the counterintuitive case. If we're adding 2, we're moving to the left. Horizontal shift 2 units left. Okay? So, what does that mean for us? All that means is, if before I had the y-intercept of 1, okay, 1 or 0, 1, I'm now going to take that point 0, 1 and move it 2 units left. So now I'm going to have 1, 2, minus 2, going to have that point minus 2, 1. And so my sketch is going to now look like this, where that y-intercept is now the point, so when I plug in 0 for x, I'm going to have 4 squared, so this is 16. So my y-intercept is now the point 0, 16. Ooh, that's kind of smashed in. My y-intercept is the point 0, 16. And the horizontal asymptote, right? So before, with that vertical shift example, we move the image up and down. We end up forcing it to cross the x-axis. Here, we've just moved it left and right. It still doesn't cross the x-axis, so the horizontal asymptote is still the line y equals 0. Okay? Now, for this one, alright, so remember, if our parent function is 4 to the x, and we're negating the function, that's a reflection in the x-axis. So this is a reflection in the x-axis. This is a reflection in the x-axis, and so that means we're going to take that image and we're just going to fold it over the x-axis. So we end up getting, y. X 1. So we get a rough sketch that looks something like this. That looks something like that. All right? Where here, if before our y-intercept was 0, 1, we're going to take that point, we're going to fold it over, and unsurprisingly that means our y-intercept now becomes the point 0, -1. And again, that x-axis is still going to be the horizontal asymptote because, again, we haven't really shifted the graph up and down. We've kind of just done a fold, and so it's still keeping that same characteristic it had before, but this time, where before it was doing a decrease to an increase, or it was just increasing, now we're just decreasing in this negative region, but still the fact remains that as we get closer and closer to this x-axis, it's still never going to cross that x-axis, so the horizontal asymptote has not changed. Okay? So hopefully you managed to create similar sketches and came to similar conclusions about the y-intercept and horizontal asymptotes. So that was pretty much all I wanted to talk about in regards to the graphs of these exponential functions. Kind of really mumbled there. The graph of these exponential functions was just to introduce their common characteristics, the most important being the idea that all exponential functions have some form of a horizontal asymptote, and then just to emphasize the fact that all these translations and reflections we talked about before in a previous lecture, they still can be applied here for exponential functions. The most important note being that for vertical translations, the horizontal the horizontal asymptote changes. So vertical translations, you have a new horizontal asymptote. It is no longer at the line y = 0. But for any other translation, the horizontal asymptote doesn't change. Okay? So that is going to be it for our discussion of the graphs. Let's now briefly mention this special number e, and then get into real-world applications with compound interest, and that'll be it. So, okay, so let's briefly talk about e. So e is like pi. It's a very special type of number, right? So it's an irrational number. E equals, or is approximately the value 2.7182818. Forgot an 8. 1828, blah, 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 right? I'm never going to expect you to know what this number value is, just again want to emphasize the fact that e, whenever we use it, is a number value. It's not an exponent, it's not a variable, my bad, it's not a variable, could be an exponent, but it is a number value. It is fixed, it is constant. It's known as Euler's number, and Euler is arguably one of the most famous mathematicians. For any of you who go to calculus, you're going to hear him a lot. What's more important for us is that e is also known as the natural base. Again, going back to base being the number value in an exponential function, so something like e to the x. Again, actually, referring back to calculus, for any of you who are going to move on to calculus, e can actually be calculated. The value of e can be found from the following limit. The limit as n approaches infinity of 1 plus 1 over n is the power of n. For those of you unfamiliar with limits, all limits basically are, in their most simplified form, is take some variable, n in this case, keep on plugging in numbers for n, and keep on plugging in numbers and approach infinity, so keep on plugging in bigger and bigger numbers. And what you'll see is that with each successive number you plug in, as you plug in bigger and bigger numbers, this equation right here will approach this number value. All right. So theoretically, you plug in the biggest number you could ever think of into this formula, and it'll look something like this. That's the general idea behind limits. Okay. Yeah. So this is actually a very heavy calculus-based idea. Just writing this one line. Is going to be something you probably spend maybe even half a lecture talking about in calculus. It's a very important idea right there, and it's a very interesting idea. So, yeah, but again, definitely outside the scope of this class, but felt like I should mention it. Always feel like I should mention calculus whenever it gets the chance, because calculus is awesome. But regardless, for us, just want to get to the idea and emphasize the fact that whenever we're using this value e, please remember, it's a constant, it's a fixed number, it's like pi. And why we care so much about it is because, like pi, e is just one of those mystical numbers that just shows up everywhere. It just appears. Whenever we're deriving formulas, creating models for certain things, just e is always present. It's just one of those mystical things in math that never seems to go away and is just so extremely useful. So for us, we're actually going to start using it now, and we're going to use it in relation to this idea of compound interest. So let's go ahead and talk briefly about that. Okay, so start. Alright, so for the last topic for today, what we're going to touch upon is this idea of compound interest. Alright? And why we're going to bother talking about it is that compound interest ends up being the most common or familiar real-world application of exponential functions that people will end up encountering in their day-to-day lives, right? So just to, I guess, briefly summarize compound interest is this idea of having, say, a bank account, and a bank account with a certain interest rate. And then that interest rate accruing or gaining you money as the years go on. That's the general idea of compound interest. And so that's the kind of scenario we're going to imagine when we're talking about this in regards to our classes. We're going to be talking about like bank accounts and stuff like that. And what we're going to do for today's lecture is we're going to present two different functions. And these two functions, depending on your scenario, you would use one or the other, and they would model this idea of compound interest. So again, working with the assumption that we're talking about something like a bank account, then after t years, the balance, so let me go ahead and underline as I read along the important words. So after t years, the balance in an account A with principal, and principal is just another word for the initial deposit or the initial investment. So principal P and an annual interest rate R, and that R will always be in decimals, can be modeled by the following formulas. So the first formula we're going to end up using and seeing is, and again, we're going to present two formulas. They're each going to have their own independent scenarios in which you want to use them. So for the first formula, we would use this for when we have n compounds per year. In other words, we have a fixed number of times, and we have a fixed number of times in which we add or get to accrue or add money to our account based off the interest. All right, so that n implies we have a fixed number of times we're going to compound. All right. And what the formula is that the amount in your account, A, so the amount of money we have, A will equal the principal amount, P, times 1 plus your interest rate over the amount you're going to compound, so R over n, to the power of n times t, the number of times we compounded, times the year. So after t years, I can expect the amount in my account with fixed number of compounds n to be equal to this amount. All right. So as I mentioned, we have two formulas we're going to talk about. This is the formula for a fixed number of compounds. Let's now discuss what the formula is for when we compound with without a fixed amount, where we just let ourselves compound as much as we want to. So let's talk about that now. All right. So again, right, the formula we have right now tells us how much we have in our account after we compound our interest for a fixed number of times, that being n, so a fixed number of times in a given year. So the question then stands is, what changes if we don't fix the number of times we compound? We just let ourselves compound as much as we want during a given year. So how does that change the formula we're looking at? Well, in order to talk about that, we've got to be a bit tricky before we get into that discussion. And how we're going to be a bit tricky is we're going to do this. We're going to let m equal r, or n over r. We're going to let m equal n over r, and what that's going to do is that 1 over m then is 1 over n over r, which equals r over n. Okay? That's going to be important. What's also important to note is that m times r, which is n over r, times r, just equals n. Okay? So these are two important things to note. Now, why we need to note them is because we're going to be tricky, we're going to be a bit subtle, and when we plug them into our equation 1, we get A equals P times 1, and remember we have R over N, and R over N is the same as 1 over N, plus 1 over M. It's the power of NT, but NT can be the same as M to the R, M times R. So we're going to have M times R to the power of T. Alright? So basically all we've done so far is taken that original equation and substituted in this variable M through these subtle substitutions. Now why that's important for us is because, again, we're going back to the idea that we're going to let ourselves compound as much as we want in a given year, right? That's what we're now considering for this second formula. And I guess I should have said at the start of this, that right now we're going to build the second formula. So this second formula is going to be built around the fact that we're going to let ourselves compound as much as we want in a given year. That number could be big as we possibly want it to be. So in other words, and we're going to have to kind of take my word on it for, in other words, this is that scenario we're considering is the same as considering, or the same as taking the limit as m approaches infinity of this equation we wrote. All right. To kind of, I guess, convince you if you're unconvinced of why this is what we're considering, right? This m approaching infinity, this is saying let m be as big as you want it to be. Again, going back to the idea, we're just considering the scenario where we let that number of times we compound be as big as we want in a given year. We don't fix that number. So if we get this limit, then what's interesting to note is if I write parentheses like this, so if I write my parentheses like this, right, where I kind of seclude inside the parentheses all the terms that only use m, and I remember that the limit I'm using is limit as m approaches infinity, so the only things that have m inside my equation are this 1 plus 1 over m to the power of m. What's so interesting to note is that if you recall, the parts I have in red make up the exact definition for E. So what ends up becoming, what someone realized along the way, whoever knows how many years back, is that given this fixed number of compounds formula for compound interest, and if we let that number of compounds just blow up, let it go to infinity, let us compound as much times as we want in a given year, in other words, you introduce a limit to your problem, through some subtle substitutions, that limit just becomes the definition of E, and as a result, we get our second formula for compound interest, this being, excuse me for a second, this being continuous compounding, right? We're not fixing that number of compounds and just applying that definition to the limits. The formula then becomes that A equals P to the ERT. And that's how we get our second formula, is by using that definition of E, and that it is a limit value. Okay? So this is for continuous compounding, and there is our second formula. So, just thought it would be cool to show you guys the derivation. This is kind of a very rough sketch of the derivation to get that formula, but thought it'd be cool to show you guys. So now let's go ahead and actually use these two formulas in some examples. Okay, right, so we've now established our two formulas for compound interest. They're used in two different scenarios. If we have a fixed number of compounds in a year, then we use the first equation, which is that A equals P times 1 plus R over N to the power of NT. Now, the other formula is when we have an unfixed number of compounds, or in other words, where we let ourselves compound continuously in a given year. In that case, we use the formula A equals P times E to the power RT. All right, so let's now consider the following example then. The example goes like this. You invest $6,000 at the start, you invest $6,000 at an annual interest rate of 4%. All right, so we're investing in a bank account, let's say. Find the balance after 7 years when compounded And for the first part of the example, we're going to say when we compound quarterly. So, first things first when we're doing these problems is we read it, and through the wording of the problem, we understand and we identify this is a compound interest problem, right? I know it's kind of obvious since that's what we're kind of talking about, but like on an exam or something, you would identify this is a compound interest problem. I mean, quite simply, it has the word compound in there. You're talking about investments, things like that. So that's how we identify it's a compound interest problem. From there, the next thing we need to identify is which formula are we going to use? Are we going to use our, actually, you know what? Yeah, first thing we need to identify next is which formula we're going to use. Are we going to use our fixed number of compounds formula, or are we going to use our continuous compounding formula? And the question to that answer heavily depends on the wording of your problem. So for us, the answer comes in this first part A, where we're saying we're going to compound quarterly, right? So the fact that we're compounding quarterly, this fixes the number of compounds. So we identify that for at least this first part of our example, we're going to be using the first equation because we have fixed the number of compounds, we have fixed it to a quarterly amount. So from there, as always when we're doing equations that are models, every variable in our equation has a meaning, right? A has a meaning, P has a meaning, R, N, and T all have meanings. A is the amount in our accounts. P is the amount we initially invest. R is the interest rate. N is the number of times we compound, and T is the years. So with that in mind, we need to then work through our word problem and identify the proper values for each variable. Right? So A, let's start with A. What's the amount we have in our accounts? Well, we read through our problem. You invest $6,000 at an annual interest rate of 4%, find the balance after 7 years when compounded quarterly, right? Again, I guess I kind of forgot it, but whenever we're doing word problems, we're looking for the goal of the problem. And the goal is right here. We want to find the balance. A is our balance. In other words, we're trying to solve for A. It's our unknown. Okay, next we go through, we pull out the next piece of information we can. We start at the top of the problem. You invest $6,000. There it is. There's our initial investment. We're starting with $6,000. That's our value for P. Okay? And we invest at an annual interest rate of 4%. There you go. There's that word rates. That's our variable R. So our rate is 4%. Now remember, when I first introduced these equations, I said that R is always in decimals. In other words, I want to convert that 4% to decimals. So we need to convert that to decimals. Remember, decimals aren't numbers. That was horribly wrong what I just said. Percentages aren't numbers. We need to convert this percentage to a number, and so that simply means all we need to do is divide by 100. So we get 0.004. That is our R. R is not 4, R is 0.004. And then moving forward from there, next we need to identify T, right? So we use this piece of information, we use this piece of information. Here's another piece of information we can use. After 7 years, so that gives us our time frame. T is 7. And then lastly, we need to identify N, the amount of times we're compounding in a given year. So that's going to be this quarterly statement right here. And for problems like this, this is kind of have to go back and use our English knowledge. So we have to identify that the word quarterly, quarter heavily implied with 4, so N is going to equal 4 in this case. Okay, so now we've identified all our variables, their proper amounts, so now all it simply becomes is a matter of plugging into our formula and solving for it. Just a simple plug and chug exercise. So, as you can see, I've run out of room though, so I'm going to need to erase in order to, just going to erase this blue part right here. So, go and pause the video to get these variable deck relations written down, and then we'll just plug it into our formula. So go ahead and do that now. Okay, so now that we have the numbers, we can go and plug into our formula, and that's going to tell us that A is going to equal 6,000 times 1 plus 0.004 divided by 4, all to the power of 4 times 7. And that will be the amount in our account after 7 years with a quarterly compound on that account. So now we just go and plug and chug. So we're going to get 6,000 plus divided by 4, all to the power of 4 times 7. And we're going to get approximately 6,170.29, let's call it. This will be the amount we have in our account after 7 years. Again, right, not going to be able to do that number by hand. It's going to be practically impossible for us to do that number by hand. We're going to need to use a calculator. So again, if you're unfamiliar with how to use a calculator, a scientific calculator in particular, please look it up either through Google or YouTube, or schedule a Zoom meeting with me, and I'd be more than happy to walk you through your calculator. But there you go. There's our first example. I don't know, I lost my train of thought there. But here's our first example. Again, it wasn't too hard to do. All we had to start with the problem was we were presented the word problem, we read through the word problem, we identified the keywords of invest and compound. That tells us, okay, this is going to be a compound interest problem. Once I understand it's compound interest, I understand that I'm talking about one of two formulas, the fixed number of compounds or the continuous compound. So I read through my wording again and identified that it told me I was compounding quarterly. That's a fixed amount. Therefore, I'm using my first formula. Once I identify I'm using my first formula, walk through each variable, trying to assign the proper number values with each variable. Of course, recognizing that we are solving for A, it is our unknown. And once I've done that, it becomes a simple plug and chug problem, needing to use a calculator because it's going to be hard to do by hand. And this is the end result we get. So let's go ahead and try our next example. Same premise, but the part that's going to change is right here. So if you haven't copied this portion down, go ahead and do so now. Okay, so again, same premise, but this time we are going to compound. We're going to compound monthly. Okay? So now I want you guys to go and pause the video, work this through on your own, and try to see if you can get an answer. So go ahead and do so now. Okay, so hopefully you worked through the problem and you got an answer. The answer I got was that A will equal 024.04. So this is the answer that I got. So go ahead and compare with my work. Hopefully we got the same thing. If not, definitely send me an email and we can talk about it. So, and I guess I should call this part B of the problem. So we're now compounding monthly. Again, I guess I should iterate this one part. Monthly, moving back to that English definition, right? The number of times we're compounding for this problem will be n equals 12, because there's 12 months. So if you struggle with that part, there's a hint. Still encourage you then to go and see if you got that same answer that I got. With that out of the way, let's move on to the third part of this example, where instead of doing compounding monthly, we're now going to compound, and I guess go and pause the video now to write that answer down. Okay, so now for the third and final part of this example, same premise still, but instead of compounding monthly, let's now compound continuously. Okay, so if we compound continuously, then we are now moving forward to our second formula because we have no longer fixed the number of times we'll compound. We're going to let ourselves do as much as we want. So since we are now using the second formula, no big deal. We still walk through with plugging in the known values. And we're going to get Oh. Would you look at that? Would you look at that? Actually, going back to problem B, I just found out I did a mistake. So sorry about that. Let me. I actually did make a mistake. Good thing I caught it this time. Didn't leave you guys confused. Going back to the monthly example, I guess let me just walk through it, just so I can clear up any confusion anyone had. Sorry about this. So for the monthly example, right, using that English meaning, n is going to have to be 12 if we're compounding monthly. All right. So that means A equals 6,000 times the value 1 plus the rate, 0.004, divided by the number of compounds, 12, to the power of 12 times 7, because we're compounding after, or we're considering this after 7 years. Okay, and this answer is 6170.35, let's say. Sorry about that again. Happy I caught that mistake at the very least. This is the new answer I get. And that makes a lot more sense intuitively. I should have noticed the other one. Regardless, this is the monthly example. Now let's try doing the continuous example. Let's go back to that. I will give a moment for everyone to pause to copy this down though. Okay. Now let's do the continuous example. Okay, so if we let ourselves compound continuously, again, same idea holds. We are no longer fixing the number of compounds. That means we're now using the second formula. So plugging in our known values into the second formula gets us that 6,000 times e to the power of 0.004 times 7. Okay, and what I wanted to talk about for this problem in particular is, again, we need to understand how to plug this value into our calculator. So first and foremost, if you don't know how to do it already, please make sure you are clear on how to access the value e on your calculator. Like for mine, I have a second, and then there's an ln button, and above that ln written in blue is e to the x. That's the button what I'm going to use here in my calculator. So it's like, if I can just draw it, it's like seconds, and then there's a button ln, and then above that button is written e to the x. So what I'm going to do for my calculator is I'm going to press second ln, and that's going to let me access e to the x. So I'm going to do 6,000 second e to the x 0.004 times 7. And that's going to give me, again, 6170.37, we'll call it. Alright, so that's the value I got. Again, just want to emphasize, because we're going to need to be doing it from now on. If you already don't know how to access this on a scientific calculator, right? It's very easy to do on a graphing calculator, but graphing calculators are not allowed for our exams. So make sure you understand how to do it on a scientific. If you don't, ask me and I'm more than happy to show you, or just look up some YouTube videos on it. Regardless, that's what we get for compounding continuously after 7 years. And it is actually worth noting, and I encourage you to think about it on your own, is that we have very similar answers for all 3 different compounds. And again, this stuff has heavy real-world meaning in regards to investments and stuff like that. So it's actually worth our time. I encourage you all to do a bit of your own research and think about the differences between these 3 different types of compounds for interest rates and stuff like that. So when you encounter in the real world, you kind of have an idea of what you would like to see for your own bank account or anything like that. But regardless, let's go ahead and move on to our next example. Okay, so for our next example, let's consider this following scenario. You deposit a lump sum, P, in a trust fund on the day your child is born. So you deposit on the day your child is born. The fund earns 6.5% interest compounded continuously. So you have 6.5 interest, and that's compounded continuously. Find the amount P, alright, so there's that goal. It's telling us we want to find P. Find the amount P, which will yield an account balance of $7,500 100,000 on your child's 25th birthday. Okay? So, already we can understand this is a compound interest problem. This is going to be a problem that uses the second formula because we are compounding continuously. And unlike our previous example where we were finding the amount in our accounts, we know the amount in our account after a certain amount of time. We want to understand what was the amount we started with. So we're going to solve for P. So, with that out of the way, or with that said, going to need the board space, as you can clearly see. This just writing the problem took up the whole board. So please pause the video, copy this question down, and also copy down the parts underlined, because these are the key phrases and words in the problem that we need to take note of. And once you do that, we'll go ahead and we'll walk through this problem. Okay, so just to list the important information again, right? We are trying to solve for P. We're trying to understand what our initial investment was. We understand that in our account we have 7,500,000, and that this is occurring after 25 years. All right, and also the interest rate in our account is 6.5%, but of course we don't use percentages. We convert this to a decimal by dividing by 100, and we get that our rate is 0.0065. So then, most importantly, when we read the problem, we understood that this was a continuous compound scenario. That means we are using our second equation of A equals P times e to the RT. All right. Then plugging in the relevant information, or the known information, we get that 7,500,000 equals P times e to the 0.0065 times 25. And now it's simply a matter of solving for P. Again, we're going to need to use a calculator to understand what this number is. Not going to be able to calculate it by hand. So, using our calculator, we get that this is P times, and if we use our scientific calculator, it gives us 1.17645, let's call it. So, I guess it is important to note, and I should discuss this, I did round here, so I rounded. And in regards to you guys, because we're going to have to round these numbers, these usually decimal numbers that never stop, that go on forever. So when we're doing it for our class, let's try to always keep 3 decimal places. So when you guys are doing homework and stuff, always try to round to 3 decimal places. Actually, on that note, for WebAssign will actually tell you how many decimal places it wants. So when you're doing your work, always try to keep a couple more numbers past the decimal spot WebAssign wants. And the reason why you want to do that is if you round exactly to what WebAssign wants, as you're working through the problem, you're going to be introducing error. So try to give yourself a couple more decimal places to account for that error. But regardless, moving forward on exams and stuff like that, just make it 3 unless I state otherwise. I have a 5 here, but that's just because it rounded nicely at the 5th decimal spot. But regardless, moving forward, we still want to solve for P, so we got to divide over, and this is going to give us that P is equal to, so 7,500,000 divided by 1.17645 gives us approximately 637,511.156, let's say. So that was the amount we initially invested into our account. Okay? So, again, these formulas aren't hard to use. Just got to make sure we are clear on their definition of the formulas, what each variable means, so that when we're reading the problem, we understand what numbers need to be assigned where. That's the most challenging part, I would say. The second most challenging part, but quickly learned, is just how to actually solve these numbers by using our calculator. Again, a quick Google search or just talking with me briefly through Zoom can fix that issue if you are struggling with how to calculate these more awkward numbers using our calculator. But short of that, that's it for today's lecture. Hope everyone is still continuing to stay safe, and I think I said that twice. Still continuing to stay healthy, still continuing to stay safe, and I'll catch you guys in the next video. See you then.